Welcome to the Sleepy Astronomer, a place where science drifts gently into dreams. Tonight, we journey across the cosmos to explore the life and death of stars. From their quiet beginnings in cold clouds of dust, to their dazzling finales as supernovae, black holes, and beyond. As you settle in, feel free to share with us. Where in the world are you watching from? Whether under city lights or countryside stars, you are part of this beautiful universe too. Now take a deep breath. Let the stars guide you to sleep. In the vast, dark canvas of the universe, where silence reigns and time stretches beyond imagination, there are quiet places filled not with light, but with potential. These are the nurseries of the cosmos, cold, dark clouds made of gas and dust, known as nebulas. Unlike the dazzling stars and galaxies we often admire, nebulas are mysterious and shadowy. They are not yet stars, but the silent beginnings of something extraordinary. If you could drift slowly through one of these clouds, you might not see much at first. The gas is thin, spread out over hundreds of light years. Yet these clouds are immense, so large they could swallow entire solar systems. They are mostly made of hydrogen, the simplest and most abundant element in the universe, along with traces of helium and tiny flecks of cosmic dust, particles left behind from older stars that once lived, burned and died. This dust is ancient. It carries with it the memory of stars long gone, and in time it will become part of new stars, new planets, and perhaps even new life. These clouds float quietly through space for millions of years, waiting for just the right moment to stir. Often the trigger is subtle, a passing shockwave from a nearby supernova, the gravitational tug from another cloud, or even the gentle movement of the galaxy itself. Whatever the cause, something changes. The calm is broken, and slowly parts of the cloud begin to collapse under their own weight. This collapse is guided by gravity, that quiet but persistent force that binds the universe together. As certain regions of the nebula become denser, gravity pulls in more and more material. The gas and dust swirl inward, coiling like mist in a dream, forming dense knots called cores. Inside these invisible cocoons, something miraculous begins to happen. Heat. As the gas falls inward, it compresses and heats up. The temperature in the core begins to rise, quietly, steadily, like a candle being lit deep within a cave. The cloud may look still from the outside, but deep within, change is accelerating. These collapsing cores are the very first steps in the birth of stars. For now, they remain hidden, wrapped in blankets of dust so thick they block visible light. But in the infrared spectrum, we can glimpse them glowing softly, like embers beneath ash. All around, countless other cores are forming too. Some will become small, faint stars that live for trillions of years. Others will become giants, burning bright and dying young. Some will form in solitude, while others are born in crowded clusters surrounded by siblings. These stellar siblings will sometimes dance around each other for millions of years or drift apart, each following its own cosmic path. The dust in the nebula plays a special role as well. It helps cool the cloud, allowing gravity to work more efficiently. Without this dust, stars would be far harder to form. And interestingly, this same dust is made of elements like carbon, silicon, and oxygen, materials essential to life. Already, even before the star is born, the ingredients for future worlds are present. As time goes on, the centre of each collapsing core becomes hotter and denser. Eventually, it reaches a point where it glows with its own light, not yet from nuclear fusion, but from sheer heat alone. This is the protostar stage, but even before reaching that point, the nebula has already given the universe something profound, the promise of a new beginning. Nebulas are not just clouds, they are cosmic wombs, where the universe pauses, breathes, and prepares to create. They are places of silence and anticipation, of coldness and warmth beginning to stir. They remind us that even in the darkest, quietest corners of space, something beautiful can begin. And that perhaps is one of the most comforting truths of the cosmos. So as you lie back and let your thoughts drift through these starlit clouds, remember that every twinkling star you see tonight, no matter how far away, was once part of such a nebula. Cradled in the quiet, born from darkness, destined to shine. As the cold, silent cloud begins to collapse, gravity becomes the guiding hand, gently drawing material inward, atom by atom, dust grain by dust grain. This slow, inevitable pull is the heartbeat of the cosmos, and with it, something ancient and miraculous begins to unfold, the beginning of a star. Imagine a region within a nebula where the gas and dust have started to concentrate. The particles, once lazily drifting through interstellar space, now find themselves pulled together by the invisible threads of gravity. With every moment that passes, the material becomes denser, and as it does, its pull grows stronger, dragging in even more gas from the surrounding cloud. This creates a feedback loop. Gravity gathers mass, which strengthens gravity, which gathers even more mass. The process may take thousands or even millions of years, but in the vast scales of the universe, this is merely the blink of an eye. Inside this growing knot of material, the temperature begins to climb. Gas particles crash into one another more frequently and with greater force. What was once an icy cradle of darkness becomes a warm, churning sphere, a place of pressure, heat and motion. The pressure from the collapsing cloud pushes inward, while the increasing heat begins to push outward. A balance is forming, delicate and shifting. The system becomes dynamic, alive in a way it wasn't before. At this stage, the dense centre is called a protostar, a star in the making. It is not yet shining with the true light of fusion, but it is glowing faintly from the sheer pressure and heat of gravitational collapse. Deep inside, the temperature reaches thousands of degrees. The protostar is still hidden from our eyes by the thick cocoon of dust and gas surrounding it, but in infrared wavelengths, astronomers can detect its warm, developing presence. Around the protostar, the surrounding material begins to swirl. Gravity not only pulls inward, it also organizes. The rotating gas and dust flatten into a disk, spinning like a slow-motion whirlpool. This disk will eventually form planets, moons, asteroids and comets, but for now, its only job is to feed the hungry star at its centre, funneling matter into the core where it continues to grow. As more gas falls in, the protostar becomes heavier. Its core compresses further, and the temperature climbs into the tens of thousands, then hundreds of thousands of degrees. the protostar wobbles and flickers. It may release sudden bursts of energy, throwing jets of gas from its poles, thin streams of matter that can stretch for light years into space. These outflows help regulate its growth, preventing it from collapsing too quickly, while also clearing out the surrounding dust. Bit by bit, the veil begins to lift. Outside the core, pressure waves ripple through the surrounding gas, like gentle thunder in a deep fog. These waves stir nearby pockets of the nebula, sometimes triggering new rounds of collapse, creating more protostars, celestial siblings born in the same cloud. Whole star clusters can be born this way, connected by origin, though each will follow its own path through the galaxy. Meanwhile, inside the protostar, something extraordinary is on the horizon. As the temperature at the core climbs to about 10 million degrees Celsius, the hydrogen atoms, which have been squeezed tightly together, begin to fuse. They merge to form helium, releasing a tremendous amount of energy. This is the moment everything changes. The star, for the first time, lights up from within, not just a glow, but a powerful radiant fire. This is nuclear fusion, the engine that will power the star for millions to billions of years. In an instant, the protostar becomes a true star, balancing the inward pull of gravity with the outward pressure of light and heat. The star is now stable, shining brightly in the darkness, a new beacon in the galaxy. The journey from dust and shadow to brilliant light is complete. The process may have taken a few million years, but it is one of the most elegant and consistent acts in nature. Every star you've ever seen, from the warm sun above you to the distant twinkles of the night sky, began its life this way. Pulled together from nothing more than dust and gas, shaped by the gentle persistence of gravity, and ignited by the hidden fire of the universe itself. And yet, the story has only just begun. The star has been born, but its journey through life, transformation, and ultimately death is still ahead. For now, it shines quietly, cradled in space, surrounded by the remnants of the cloud that gave it life. A new voice has been added to the cosmic symphony. So as you breathe softly and let your thoughts drift, imagine this process not as a distant scientific event, but as something deeply poetic. Somewhere, right now, in the cold silence between stars, another one is being born. Quietly, patiently, just as our sun once was, just as we all, in some form, came to be. The birth of a protostar marks a quiet but monumental turning point in the life of a star. Up until now, the process has been invisible to the naked eye, hidden deep within thick clouds of cosmic dust, where gravity and time do their slow and silent work. But with the formation of a protostar, the story begins to unfold more clearly. It is no longer just a cold clump of gas. It has become something more, something with identity, structure, and a growing inner fire. A protostar is not yet a full-fledged star, but it is no longer a shapeless fragment of the nebula either. It's like a child just before birth, still forming, still fragile, but already very much alive in its own mysterious way. Inside the protostar, the temperature has risen high enough to produce a dim, reddish glow, not from nuclear fusion, but from gravitational energy. The immense pressure from the inward collapse causes the gas at the centre to heat up and emit radiation. It glows, not unlike the coals of a dying fire, quietly burning in the darkness. Surrounding the protostar is a thick, swirling disk of gas and dust. This rotating disk plays a vital role, not only in feeding the growing star, but in shaping the future of entire planetary systems. Particles within the disk bump into each other, stick together, and slowly begin to form larger and larger clumps, some no bigger than grains of sand, others growing into kilometre-wide objects that may one day become moons or planets. These early collisions are gentle, like snowflakes piling up. They are guided by gravity, but also by the subtle, sticky forces that bind dust in space: electric charges, chemical bonds, and sheer patience. The protostar itself is often unstable during this stage. It pulses and shifts, expanding and contracting as it struggles to find balance. It may release strong stellar winds, streams of charged particles that blow outward, shaping the surrounding disk, and even carving cavities in the parent nebula. These winds help regulate the star's growth, like a child pushing back as it learns its own boundaries. They also begin to shape the surrounding space, influencing how planets, asteroids, and comets form later on. Sometimes, the protostar releases spectacular jets of gas from its poles. These jets, called Herbig-Haro objects, streak through space at hundreds of kilometers per second, lighting up the surrounding material as they crash into it. Though they are temporary, they are one of the first visible signs that a star is being born. It's as if the protostar, still wrapped in cosmic blankets, is stretching its limbs and making its presence known. Despite all this activity, the protostar still has a long way to go. Deep in its core, the temperature is still rising, hundreds of thousands of degrees, then millions. The atoms of hydrogen are moving faster and faster, but they are not yet close enough, or hot enough, to begin fusion. This is the waiting period, the preparation before ignition. During this time, the protostar continues to gather mass from its disk. Every bit of gas that spirals inwards adds weight to the core, increasing the pressure and pushing the atoms even closer together. Eventually, the pressure and temperature become so great that the hydrogen atoms start to fuse into helium. This is not a slow or gentle process. It's a powerful chain reaction that releases a tremendous amount of energy. In a single, glowing moment, the balance shifts. The outward pressure from this new source of energy pushes back against the crushing force of gravity, and for the first time, equilibrium is achieved. The star stops collapsing and begins to shine steadily. Fusion has begun, and a star is truly born. But even before that moment, the protostar has already made an impact. It has carved out a space for itself in the galaxy. It has gathered material from the nebula, released light and heat, and perhaps even begun to shape the architecture of a future solar system. It is still wrapped in mystery, still changing, but it is unmistakably alive. From Earth, we cannot see these early stages with the naked eye, but telescopes that peer into the infrared can reveal these hidden stars in the making, faint, flickering dots nestled in dark clouds. They remind us that the universe is always creating, always becoming. Every protostar is a story unfolding slowly over millions of years, in the soft language of gravity, heat, and time. As you lie still and imagine the distant corners of our galaxy, think of these quiet beginnings. Somewhere, a protostar is glowing faintly in the dark, surrounded by the dust and gas that gave it life. It does not yet know what it will become. A red dwarf, a giant, or a star like our own sun. But its journey has begun. And in its first quiet light, it carries the promise of worlds not yet born, and perhaps even the seeds of life to come. Once fusion begins at the core of a star, a new chapter unfolds, one that can last for billions of years. The star enters what astronomers call the main sequence, a long and stable phase where it quietly burns hydrogen into helium, producing light and warmth. This is the calm, luminous heartbeat of the cosmos. Nearly every star you see in the night sky, including our own sun, is in this stage of life, a golden age of balance, brightness, and beauty. The main sequence is a period of harmony. In the heart of the star, a delicate but powerful balance has been achieved. The inward pull of gravity is perfectly counteracted by the outward push of energy from fusion. Every second, immense amounts of hydrogen atoms are fusing to form helium, and in the process, releasing radiant energy that streams outward to the surface. This energy then travels across space, lighting up planets, warming moons, and piercing the cold darkness of the void. Stars can remain in this stage for a very long time. For small stars like red dwarfs, this phase can last for trillions of years, far longer than the current age of the universe. Larger stars burn more brightly, but also more rapidly. A star like our Sun will reign on the main sequence for about 10 billion years. More massive stars, blue giants for example, burn with extraordinary brilliance, but exhaust their fuel in only a few million years. Like candles burning at both ends, their intensity comes at a cost. The colour of a main sequence star tells us much about its character. Smaller, cooler stars appear red or orange. Medium-sized stars like the Sun glow in a soft yellow-white, and the most massive and hottest stars blaze blue-white, their light sharp and dazzling. Each of these colours corresponds to the star's temperature, and each temperature reflects the speed at which fusion is occurring in its core. Despite their steady appearance, stars on the main sequence are not motionless or unchanging. Deep within, their cores are slowly shifting. As hydrogen is converted into helium, the composition of the core changes. Helium is denser than hydrogen, so it accumulates at the centre, increasing the core's pressure and temperature over time. This causes the star to gradually grow brighter and slightly larger as it ages, even during this stable phase. In addition to the fusion at their cores, main sequence stars often have dynamic outer layers. Their surfaces are roiling seas of plasma, superheated, electrically charged gases. These layers boil and churn with convection currents, transporting energy from the interior to the surface, where it escapes as light. Some stars have sunspots, magnetic storms, and even solar flares that burst outward with sudden intensity, flinging charged particles across space. Our own Sun, quietly burning 93 million miles away, is the best example of a main sequence star. It is the source of all life on Earth, providing the light that plants use to grow, and the warmth that keeps our oceans from freezing. Every sunrise is a gift from a star in this stage, and it has been giving us that gift for nearly 5 billion years. In that time, it has barely changed to our eyes, yet deep within, its hydrogen reserves are slowly dwindling. Main sequence stars are also architects of the cosmos. Their gravity shapes the orbits of planets, asteroids, and comets. Their light reflects off icy moons and rings of gas, creating beauty across the solar systems they rule. They maintain the temperatures of worlds, determine whether oceans can exist, and set the rhythms of days and years. In every way, they are the stable centres around which the rest of the cosmic drama unfolds. And yet, this phase, long and luminous as it may be, is not forever. A star's time on the main sequence is limited by the amount of hydrogen in its core. When that hydrogen begins to run out, the balance is broken. Fusion slows, gravity begins to win, and the peaceful equilibrium starts to collapse. The star begins to change, but that story belongs to another chapter. For now, imagine a main sequence star quietly burning in a distant part of the galaxy. It may be surrounded by planets, or drifting alone in the void. Its light may take centuries to reach us, arriving at last to twinkle softly in your night sky. That light has travelled across time and space, carrying with it the story of a stable, glowing heart. One that, like our own sun, is patiently and silently giving life to everything it touches. So as you rest, breathe slowly and imagine yourself floating in the quiet gravity of such a star. Steady, warm, and radiant. A glowing anchor in the dark. A light that will not flicker or fade for a very long time. Our sun, that familiar glowing orb, warming our days and guiding the cycles of life on Earth, is often thought of as eternal, unchanging, and forever bright. Yet in the vast timeline of the cosmos, the sun is actually in the middle of its life, neither young nor old, but somewhere in a graceful middle age. This middle period, known as the main sequence, is where the sun has spent the majority of its existence, quietly fusing hydrogen into helium in its core and radiating light and warmth across the solar system. But this steady brilliance is just one chapter in a much longer story. The sun formed about 4.6 billion years ago, born from a giant molecular cloud not unlike the nebulas we have explored. It was once a protostar wrapped in a cocoon of dust and gas, gradually igniting as the fusion furnace in its core began to burn. Since that moment, it has settled into a relatively stable phase, a steady rhythm of nuclear fusion powering its glow, maintaining a delicate balance between the inward pull of gravity and the outward pressure of radiation. In many ways, the sun's middle age is a peaceful era. It is neither a turbulent infant nor a dying giant. During this time, its size, brightness, and surface temperature remain fairly constant, allowing life on Earth to flourish. The sun shines with a warm, yellow-white light, bathing our planet in energy that fuels photosynthesis, drives weather patterns, and sustains oceans. Without this long, stable middle phase, complex life as we know it could not exist. However, the sun's calm exterior hides a slow but inevitable change. Deep in its core, the supply of hydrogen, the sun's primary fuel, is gradually decreasing. Each second, millions of tons of hydrogen atoms fuse into helium, and the helium accumulates as a dense core that cannot sustain fusion. Over billions of years, this subtle shift affects the Sun's structure and energy output. As the hydrogen fuel begins to dwindle, the core contracts under gravity's relentless grip, causing its temperature to rise. This increased pressure heats the surrounding hydrogen-rich layers, causing fusion to occur in a shell around the core. The energy produced in this shell pushes outward, causing the outer layers of the Sun to expand slowly. This expansion marks the beginning of the Sun's journey away from its stable middle age toward its eventual transformation into a red giant. Though these changes happen over immense spans of time, they subtly alter the Sun's brightness and size. In a billion years, the Sun is expected to be about 10% brighter than it is today, warming Earth and other planets more intensely. Eventually, the Sun will swell, becoming so large that its outer layers may reach the orbit of Venus or even Earth itself, engulfing the inner planets in a glowing inferno. Yet these distant transformations do not diminish the significance of the Sun's present stage. This middle age is a rare and precious window in a star's life, a long period of calm and constancy amid the universe's grand cycles of birth, change and death. For billions of years, the Sun has been a reliable beacon, a steady light in the sky, and the heart of our solar system. Our Sun's story is a reminder that even in vast cosmic scales, stars have lifetimes filled with phases, beginnings, middles, and endings, each with its own beauty and purpose. Right now, the Sun is neither young nor old, but in the prime of its life, shining steadily and patiently. It is a star whose warmth and light have witnessed the rise of life on Earth, and will continue to nurture it for eons to come. So as you drift towards sleep, picture the Sun not as a distant, untouchable ball of fire, but as a middle-aged companion, steadily shining, quietly supporting, and enduring in its cosmic role. The Sun is the star that lights our days and guides our seasons, a glowing reminder that even in the vast universe, some things remain constant long enough to give us life and light. When we gaze up at the night sky, the stars appear as tiny points of light, twinkling softly against the velvet darkness. But their colours vary widely, and these colours tell a fascinating story about the nature of each star, about its temperature, and the processes happening deep within its blazing core. The glow of a star is not simply a pretty sight. It is a language that the universe uses to share secrets about the life of these distant suns. The colour of a star is primarily determined by its surface temperature. Hotter stars emit light with shorter wavelengths, which our eyes perceive as blue or white. Cooler stars emit light with longer wavelengths, appearing orange, red, or even deep crimson. This means that when you look at a star's colour, you're actually seeing the heat radiating from its surface. The hottest stars are massive and rare, burning at temperatures exceeding 30,000 degrees Celsius. These stars shine with a brilliant blue or blue-white light. Their intense heat means they burn fuel rapidly, living fast and bright, but often dying young in spectacular explosions. These stars dominate young star clusters and create some of the most beautiful and energetic sights in the universe. In contrast, stars with cooler surfaces, like red dwarfs, burn at a gentler temperature, often below 4,000 degrees Celsius. these stars emit a warm, reddish glow. Although less flashy, they are the most common stars in our galaxy, and their longevity is unmatched, often lasting trillions of years. The soft, steady light of a red dwarf might seem modest, but it is a testament to endurance and quiet persistence in the cosmic dance. Stars like our Sun fall in the middle of this spectrum, with surface temperatures around 5,100 degrees Celsius, glowing with a steady yellow-white light. This balance of heat and colour supports the delicate ecosystems on planets like Earth, where life depends on the Sun's steady warmth and light. Beyond temperature, the colour of a star can also reveal details about its composition. Certain elements absorb or emit light at specific wavelengths, creating subtle shifts in colour that astronomers can detect using special instruments called spectrometers. These shifts allow scientists to identify what elements are present in the star's atmosphere, revealing clues about the star's origin and even the processes unfolding within. As stars age, their colours can change. For instance, a star that has exhausted much of its hydrogen fuel may expand and cool, turning from a hot yellow or white star into a cooler, more luminous red giant. This transformation is reflected in the star's shifting colour, signalling a new phase in its life story. Some stars display peculiar colours due to unique conditions. For example, stars surrounded by thick clouds of dust may appear dimmer and redder as dust scatters shorter wavelengths of light more than longer ones. This cosmic reddening can tell astronomers about the environment surrounding the star and the presence of material that might eventually form planets. In clusters where many stars are born together, a stunning palette of colours emerges. Young, massive blue stars shine fiercely beside cooler, older red stars, painting a rich tapestry across the sky. This diversity in colour mirrors the life cycles of stars, from their energetic youth to their mellow maturity. The twinkle you see when you look at stars is caused not by the stars themselves, but by Earth's atmosphere, which bends and distorts the starlight as it passes through layers of air. This flickering effect adds a magical shimmer, making the stars feel alive and ever-changing, even though their colours are constant. So next time you gaze up at the night sky, take a moment to notice the colours of the stars. Each hue is a whisper from the universe, telling you about the star's heat, its age, and its place in the cosmic story. The gentle red glow of a distant dwarf, the brilliant blue flash of a massive giant, and the soft yellow radiance of our sun, all are chapters in a grand tale written in light. As you settle into rest, imagine drifting among these colourful lights, travelling through a sea of radiant energy, each star a beacon glowing with its own unique story. In the quiet of night, their colours become a soothing lullaby, reminding you that even in the vastness of space, every star shines with meaning, warmth, and beauty. The fate of a star is intricately tied to its mass, the amount of matter it contains from birth. From the moment a star forms in a swirling cloud of gas and dust, its mass sets the course for everything that follows: how bright it will shine, how long it will live, and ultimately, how it will die. Mass is, in essence, the script written before the star even flickers to life, shaping its destiny in the grand cosmic theatre. In the earliest moments of star formation, the core of gas and dust that begins to collapse under gravity gathers matter from its surroundings. The more material it collects, the greater its mass. This initial weight determines the star's internal pressure and temperature, which in turn controls the rate of nuclear fusion deep inside its heart. Massive stars, containing many times the mass of our Sun, experience intense pressure and heat. Their fusion reactions ablaze fiercely, producing enormous amounts of energy in a relatively short time. Because they burn fuel so quickly, massive stars live fast and die young. Their brilliant blue-white light outshines smaller stars, but their fuel reserves are consumed rapidly. Some giants may live only a few million years, a mere heartbeat in the cosmic timeline, before exhausting their fuel and collapsing under their own weight in spectacular supernova explosions. On the other end of the scale are the smallest stars, red dwarfs, that pack far less mass. These stars burn their fuel slowly and efficiently. With cooler cores and lower pressure, fusion happens at a gentle pace, allowing red dwarfs to live for trillions of years, far longer than the current age of the universe. Their light is faint and reddish, but their endurance is unmatched. Stars of average mass, like our Sun, sit somewhere between these extremes. They shine steadily for billions of years, balancing their internal pressures in a slow dance of fusion and gravity. Their lives are measured in billions of years, long enough for complex planetary systems and, on at least one planet, life to arise. But mass does more than determine lifespan and brightness. It also governs how a star evolves after it has used up the hydrogen fuel in its core. Once the core hydrogen runs low, the star begins to change, and its mass dictates what form that change will take. For stars with mass similar to the Sun, the next phase is becoming a red giant. The core contracts and heats up, while the outer layers expand and cool, swelling many times larger than before. These stars shed their outer layers gently, creating glowing shells of gas called planetary nebulae. At the end of this process, the core remains as a dense, fading ember, a white dwarf, that slowly cools over billions of years. Massive stars follow a far more dramatic path. When their core hydrogen is depleted, fusion ignites heavier elements in a series of stages: helium, carbon, neon, oxygen, and so on, each producing new energy and new layers within the star. This layered onion-like structure grows unstable until the iron core collapses catastrophically. The resulting supernova explosion is one of the most energetic events in the universe, briefly outshining entire galaxies. The remnants of these explosions depend again on the star's mass. Some become neutron stars, ultra-dense objects made mostly of neutrons, packing more mass than the Sun into a sphere no larger than a city. Others, if massive enough, collapse into black holes, regions where gravity is so strong that not even light can escape. Even the fate of any planets orbiting these stars is linked to the star's mass and evolution. Around smaller stars, planets may survive the star's long, stable life and gentle death. Around massive stars, planets may be destroyed or ejected during the star's violent end. The cosmic interplay of mass and gravity is a reminder of the universe's subtle balance. The very quantity of matter gathered in the earliest moments of a star's formation determines not only its brightness and lifespan, but its entire life story, from peaceful youth to fiery death. Mass sets the tempo of a star's life, its struggles and triumphs, and its ultimate contribution to the cosmos. So as you close your eyes and drift towards sleep, imagine a cosmic scale where the weight of stardust and gas dictates the fate of celestial giants and humble dwarfs alike. Mass is the unseen hand guiding stars through birth, life, and death, writing a story in light and shadow across the universe, from the faintest flicker to the brightest blaze. As a star exhausts the hydrogen fuel in its core, a profound transformation begins. A change both majestic and inevitable, no longer able to sustain the steady fusion that once balanced its inward gravity. The star enters a new and turbulent phase, swelling into a red giant. This stage is one of expansion, cooling, and dazzling brilliance, signalling that the star's life is moving toward its twilight years. Imagine a star like our Sun, having burned steadily for billions of years, now running low on the core hydrogen that fueled its long, stable existence. Without enough hydrogen to fuse, the core begins to contract under the immense pull of gravity. This contraction raises the core's temperature and pressure, igniting a shell of hydrogen surrounding the core. Fusion now happens not in the centre, but in a glowing shell around the shrinking core. The energy from this shell causes the star's outer layers to puff up dramatically. The star's size can swell to hundreds of times its original diameter, expanding so much that it may engulf nearby planets. Though the surface cools and the star takes on a deep reddish hue, its overall luminosity increases, sometimes shining thousands of times brighter than before. This glowing giant dominates the surrounding space, a bright and mighty presence against the dark canvas of the cosmos. The red colour of the giant star is a result of its cooler surface temperature. As the star's outer envelope expands, it spreads its energy over a much larger area, lowering the temperature of the visible surface. This cooler temperature causes the star to emit light that peaks in the red and orange parts of the spectrum. The warm, glowing red is a beautiful, serene glow, yet it marks a restless star in the midst of change. Inside the star, complex processes unfold. The core, now mostly helium, continues to contract and heat up. Eventually, when it reaches the critical temperature, helium fusion ignites, transforming helium into carbon and oxygen in a process known as the helium flash. This phase brings new energy to the star's interior, briefly stabilizing it. But this calm is temporary. The red giant phase is also a time of instability and shedding. Pulsations ripple through the star's extended atmosphere, causing it to expand and contract rhythmically. These pulsations can drive powerful stellar winds, blowing off layers of gas into space. Over time, the star loses a significant portion of its mass in these gentle but persistent outflows. The material cast off forms magnificent clouds of glowing gas around the star, destined to become planetary nebula, cosmic sculptures of light and colour. For stars a few times the mass of our Sun or less, this red giant phase marks the beginning of their final farewell. The outer layers, lost to space, enrich the surrounding interstellar medium with heavier elements, carbon, oxygen, and nitrogen, that will one day become part of new stars, planets, and even life. The star's core, now exposed and glowing white hot, will slowly cool and fade as a white dwarf, a dense ember in the cosmic night. More massive stars may follow a more dramatic path after their red giant phase. They can continue fusing heavier elements, creating layered interiors like cosmic onions. These stars end their lives in supernova explosions, violent bursts that scatter stellar material far and wide, seeding the universe with elements vital for life and new beginnings. The red giant phase is a powerful reminder of the impermanence and transformation that define the cosmos. It is a period of both beauty and decay, where a star's gentle glow expands into a majestic blaze, then fades into the quiet aftermath. The red giant stands as a symbol of change, of endings that bring new beginnings, of life that enriches death. As you settle deeper into rest, imagine floating beside such a star, immense and glowing, its warm red light spreading softly through the darkness. It is a giant nearing the end of its journey, yet still full of energy and purpose. In its light, see the cycles of the universe reflected, the constant dance of birth, growth, and eventual transformation. This is the story of the red giant, a shining, swelling presence, a beacon of change, a star embracing its destiny with quiet grandeur in the endless night. As a star like our sun approaches the final chapters of its life, it undergoes a gentle but profound transformation that marks the closing of its active, fiery existence. After swelling into a red giant and shedding much of its outer layers, the star leaves behind a dense, compact core, a white dwarf that glows faintly with the residual heat of its former brilliance. Around this ember, the material cast off during its final breaths forms a glowing shell of gas and dust, creating what we call a planetary nebula. This serene and beautiful phase is a peaceful passing, a star's quiet farewell before it slips into cosmic silence. The white dwarf is an extraordinary object. Though it contains roughly the mass of our Sun, it is compressed into a volume similar to that of Earth, making it incredibly dense. Imagine squeezing the entire Sun down to a size smaller than our planet. This is the nature of a white dwarf. At its surface, temperatures can reach hundreds of thousands of degrees Celsius, causing it to shine with a soft white or bluish light. Yet it no longer produces energy through fusion. Instead, it slowly cools, radiating away the heat left from its long and brilliant life. Surrounding the white dwarf is the planetary nebula, a glowing, colourful cloud of gas ejected from the star during its red giant phase. The name planetary nebula is a bit of a misnomer. These clouds have nothing to do with planets, but early astronomers thought they resembled the round shapes of distant planets through their telescopes. Today, we know them to be stunning, intricate shells of ionized gas, often shaped by the star's winds and magnetic fields into delicate rings, lobes, and filaments. The gas in the planetary nebula shines because it is energized by the intense ultraviolet light emitted by the hot white dwarf at the center. This light excites the atoms in the nebula, causing them to emit light of their own in vivid reds, greens, blues, and purples. These colors paint a cosmic masterpiece, visible across vast distances and inspiring wonder in all who observe them. This phase, while beautiful, is fleeting on cosmic timescales, lasting only tens of thousands of years before the nebula disperses into space. As it fades, it enriches the interstellar medium with heavier elements, carbon, oxygen, nitrogen, crafted in the star's core and spread outward by the stellar winds. These materials become the building blocks for new stars, planets, and even life, ensuring that the star's legacy continues in the universe's ongoing cycle of creation. Meanwhile, the white dwarf at the centre begins its slow descent into darkness. Without fusion to sustain it, the star gradually cools and dims, becoming a cold, dark, black dwarf over many billions of years, an object that currently exists only in theory, as the universe is not old enough for any black dwarfs to have formed yet. This peaceful passing contrasts sharply with the violent deaths of massive stars, yet it is no less significant. The death of a sun-like star is a gentle handing off of cosmic materials, a transformation from active energy production to quiet endurance. It is a reminder that endings can be graceful, full of beauty, and woven into the fabric of future beginnings. As you rest, picture this final phase of a star's life. A bright, small white dwarf shining calmly at the centre of a colourful nebula, surrounded by clouds of glowing gas, expanding slowly into the darkness. The nebula's light shimmers softly, like the last breath of a candle flickering in the night. It is a cosmic farewell, a gentle closing act in the star's long and luminous story. In this quiet moment, the star's life echoes a universal truth, that even as things fade and change, they contribute to the endless dance of matter and energy, lighting the path for what is yet to come. For some stars, particularly those much more massive than our Sun, the end of their life is anything but gentle. Instead of fading quietly as a white dwarf, these stellar giants conclude their existence in one of the most powerful and spectacular events in the universe, a supernova explosion. This dramatic farewell is a dazzling release of energy that briefly outshines entire galaxies, lighting up the cosmos with a brilliance that can be seen across billions of light years. The path to a supernova begins deep inside the core of a massive star. After burning through its hydrogen fuel, the star begins fusing heavier elements in a succession of stages: helium, carbon, neon, oxygen, silicon, each fusion process creating new elements and layers within the star like the layers of an onion. These nuclear reactions produce energy that supports the star against the crushing force of gravity, but this process cannot continue indefinitely. Eventually, the star's core builds up iron, a unique element in the life of a star, because fusing iron consumes energy rather than releasing it. Once iron accumulates, the star loses its main source of outward pressure from fusion. Gravity takes over completely, causing the core to collapse in a matter of seconds. This collapse is unimaginably rapid and violent. The core compresses until it reaches densities similar to those found in an atomic nucleus, forming a neutron star, or, if massive enough, collapsing further into a black hole. The outer layers of the star, no longer supported by the core's pressure, fall inward at tremendous speeds. When these infalling layers crash against the dense core, a shockwave rebounds outward, blowing the star's outer layers into space with colossal force. The result is a supernova explosion, a titanic burst of light and matter that can outshine the entire galaxy it inhabits for days or weeks. Supernovae are among the most energetic phenomena in the universe. In that brief moment, They release more energy than the Sun will emit over its entire lifetime. The explosion scatters the star's enriched material, heavy elements forged in its core, far and wide, seeding the cosmos with the building blocks of planets, life, and even future stars. Elements like gold, silver, uranium, and many others owe their existence to these violent stellar deaths. The light from a supernova can travel across vast cosmic distances, reaching Earth thousands or even millions of years after the event. When astronomers observe these brilliant explosions, they gain insights into the life cycles of stars, the origins of elements, and the expansion of the universe itself. Some supernovae serve as standard candles, helping measure cosmic distances and revealing the accelerating expansion of space. The remnants of a supernova are equally fascinating. Depending on the mass of the collapsed core, what remains can be a neutron star, a dense spinning object composed mostly of neutrons, or a black hole, a region of space where gravity is so intense that not even light can escape. Surrounding these remnants is often a nebula of gas and dust, glowing with energy and shaped by the powerful shock waves from the explosion. Supernovae are both an end and a beginning. They mark the death of a star, but also the birth of new stars and planets from the enriched material they disperse. These cosmic fireworks remind us of the dynamic and ever-changing nature of the universe, where destruction and creation are intertwined in a grand, endless cycle. As you relax and let your mind wander among the stars, imagine witnessing a supernova, the sudden burst of light piercing the darkness, the shock waves rippling through space, the release of matter that will someday become part of new worlds. This explosive finale is a cosmic symphony of energy and transformation, a brilliant, breathtaking end to a star's life that echoes across time and space. In this moment, the supernova teaches us that even the most powerful endings carry within them the seeds of new beginnings. The stars may die, but their light and matter continue to shape the universe, inspiring wonder and igniting the imagination in the quiet of the night. When a massive star reaches the end of its life and explodes in a supernova, one of the most extraordinary remnants it can leave behind is a neutron star, an object so dense and strange that it challenges our understanding of physics and the very nature of matter itself. Neutron stars are among the most fascinating and extreme entities in the cosmos, tiny yet incredibly powerful, packing the mass of the Sun into a sphere no larger than a city. To understand a neutron star, imagine the star's core collapsing under gravity's overwhelming pull after exhausting its nuclear fuel. The core's collapse is so intense that protons and electrons combine to form neutrons, leaving behind a dense mass composed almost entirely of these subatomic particles. The resulting neutron star is a celestial heavyweight, with density so high that a single teaspoon of neutron star material would weigh billions of tons on Earth. Despite their small size, usually about 20 kilometers in diameter, neutron stars exert incredible gravitational forces. Their surfaces are extreme places where gravity is about 2 billion times stronger than on Earth. This gravity warps space and time around the star, creating phenomena that can only be explained by Einstein's theory of general relativity. Neutron stars also spin at astonishing speeds. When the original star's core collapses, its rotation rate increases dramatically, much like a figure skater pulling in their arms during a spin. Some neutron stars rotate hundreds of times per second, emitting beams of electromagnetic radiation from their magnetic poles. If these beams sweep past Earth, we detect pulses of radiation, leading to the discovery of pulsars. These cosmic lighthouses flash with remarkable regularity, serving as some of the universe's most precise clocks. The magnetic fields of neutron stars are equally extreme, often trillions of times stronger than Earth's magnetic field. These intense magnetic forces can power spectacular phenomena such as magnetars, neutron stars with magnetic fields so strong they can distort atoms and emit bursts of high-energy radiation that reach across the galaxy. Beneath their exotic surfaces, neutron stars hold mysteries that continue to intrigue scientists. The matter inside may exist in states never replicated on Earth, superfluid, superconducting, or even more exotic forms of dense matter. Studying neutron stars helps physicists test theories about the behavior of matter under extreme conditions, pushing the boundaries of known physics. Neutron stars do not remain unchanged forever. Over millions of years, they lose energy, slow their rotation, and cool down, fading gradually. Yet, even as they age, their extreme properties and the environments they create can influence nearby matter, such as in binary systems where neutron stars draw material from companion stars, creating energetic X-ray emissions. In the grand cosmic story, neutron stars are the dense, compact remnants of massive stellar lives, a testament to the power of gravity and the mysteries of matter. They are tiny giants, spinning beacons in the darkness, relics of explosive endings that continue to shape the universe in subtle and profound ways. As you drift into rest, imagine standing beside one of these incredible objects, so small yet so powerful, a spinning light in the vastness of space, holding within it the secrets of matter and energy at their most extreme. The neutron star is a cosmic paradox, both a remnant of destruction and a symbol of the incredible resilience and complexity woven into the fabric of the universe. When a star is born with enough mass, typically more than about 20 times that of our Sun, its life story takes a path toward one of the most mysterious and powerful phenomena in the universe: the birth of a black hole. Unlike other stellar remnants, black holes are regions of space where gravity becomes so intense that nothing, not even light, can escape their grasp. They are cosmic enigmas, places where our familiar laws of physics are pushed to their limits and beyond. The formation of a black hole begins in the heart of a massive star nearing the end of its life. After burning through successive layers of fuel, hydrogen, helium, carbon, oxygen, and beyond, the star builds up a dense core composed mostly of iron. Because iron fusion does not release energy, but instead consumes it, the star loses its ability to counterbalance gravity's inward pull. The core becomes unstable and collapses catastrophically in a matter of seconds. This collapse is unimaginably violent. The core contracts under its own gravity until it reaches an infinitely dense point known as a singularity, where the known laws of physics cease to apply. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. Once anything crosses this horizon, whether it is matter, light, or even information, it is forever trapped within the black hole. The birth of a black hole is often accompanied by a supernova explosion, where the outer layers of the star are blasted away with tremendous force, enriching the surrounding space with heavy elements. But while neutron stars remain visible as dense stellar corpses, black holes are invisible to direct observation. Instead, astronomers detect them by their effects on nearby matter and light. For example, matter spiraling into a black hole forms an accretion disk that heats up and emits powerful X-rays before crossing the event horizon. Black holes can vary widely in size. Stellar mass black holes, formed from single massive stars, may be only a few times more massive than our Sun, but compacted into a space no larger than a city. At the other extreme are supermassive black holes, millions or billions of times the Sun's mass, lurking at the centres of galaxies, including our own Milky Way. These giants shape the evolution of galaxies, influencing the motion of stars and the growth of cosmic structures on the grandest scales. Despite their ominous reputation, black holes play an essential role in the universe. They act as cosmic engines, powering phenomena such as quasars, brilliant, distant beacons powered by supermassive black holes devouring matter at incredible rates. They also help recycle matter and energy, contributing to the complex web of cosmic evolution. The mysteries of black holes continue to captivate scientists and dreamers alike. What happens inside the event horizon? How does information behave in these extreme environments? Could black holes connect to other universes or dimensions? These questions inspire some of the most exciting research in physics, bridging the realms of astrophysics, quantum mechanics, and relativity. As you relax and let your thoughts wander across the stars, imagine the birth of a black hole, a star's final, dramatic transformation into an invisible cosmic powerhouse. Picture the collapsing core shrinking beyond the point of no return, forming a boundary where gravity rules supreme and light itself is trapped. Though unseen, this powerful presence shapes the universe in profound ways. In the quiet darkness of space, black holes stand as gateways to the unknown, symbols of cosmic extremes and the limits of human understanding. They remind us that the universe is vast and mysterious, filled with wonders beyond our everyday experience. As you drift towards sleep, let the mystery of black holes inspire awe and curiosity, an invitation to explore the infinite depths of space and time. Stars are rarely solitary travellers through the vastness of space. More often than not, they are born together in groups, clusters, sharing the same cosmic nursery and bound by the gentle tug of gravity. These star clusters are stellar families, ranging from a few dozen to millions of stars, all moving together through the galaxy like celestial communities. Understanding these clusters reveals much about the life cycles of stars, the dynamics of galaxies, and the grand architecture of the cosmos. Star clusters begin their lives inside giant molecular clouds, those vast, cold nebulas rich with gas and dust where stars are born. As gravity pulls material together within these clouds, multiple stars form almost simultaneously. These sibling stars, born from the same cloud, remain gravitationally linked, orbiting a shared centre of mass. Over millions or billions of years, they drift through space as a coherent group, their fates intertwined. There are two main types of star clusters: open clusters and globular clusters. Open clusters are relatively young, loosely bound groups of hundreds to thousands of stars. They are often found in the spiral arms of galaxies, including our own Milky Way. These clusters are rich in young, bright stars and often have irregular shapes. Because they are loosely bound, open clusters gradually disperse over time, their stars drifting apart and mixing into the galaxy's general stellar population. Globular clusters, on the other hand, are ancient and densely packed. They contain hundreds of thousands to millions of stars, tightly bound by gravity into spherical shapes. These clusters orbit the outskirts of galaxies, including a halo of globular clusters surrounding the Milky Way. The stars in globular clusters are typically very old, some nearly as old as the universe itself. Their crowded environments foster unique stellar interactions, close encounters, stellar collisions, and binary star systems that shape their evolution in fascinating ways. Star clusters are laboratories for astronomers studying stellar evolution. Because all stars in a cluster form roughly at the same time and from the same material, differences among them mainly reflect variations in mass. By examining clusters, scientists can observe how stars of different masses age, change brightness, and move through different phases of their lives. This helps refine our understanding of stellar life cycles and the physical processes governing stars. Clusters also offer clues about the formation and evolution of galaxies. The distribution, age, and motion of clusters reveal how galaxies grow, interact, and sometimes collide. Globular clusters, in particular, are relics of the early universe, offering a glimpse into the conditions present shortly after the Big Bang. Within clusters, stars influence each other through gravity and radiation. Massive stars can shape their surroundings by blowing powerful winds and emitting intense ultraviolet light, triggering new waves of star formation or dispersing remaining gas. In dense environments, gravitational interactions can alter stellar orbits or even lead to mergers, producing exotic stars or compact objects like neutron stars and black holes. For any planets orbiting stars within clusters, the environment can be dynamic and sometimes hazardous. Close encounters with other stars can disrupt planetary orbits, or even eject planets into interstellar space. Yet clusters also represent fertile grounds for the potential emergence of life, as the abundance of stars increases the chances of planetary systems with the right conditions. As you settle into sleep, imagine drifting gently through a star cluster, a shimmering community of lights, each star a member of a cosmic family. Some are young and vibrant, others ancient and wise, all bound together in a delicate gravitational dance. In this stellar gathering, you sense the connectedness of the universe, the shared origins, and intertwined destinies of countless stars. Clusters remind us that in the vast loneliness of space, there is companionship, structure, and a sense of belonging. They are stellar neighborhoods where light and gravity weave stories of birth, growth, and timeless connection, an enduring testament to the harmony that shapes the universe. In the quiet of night, as you dream, picture yourself among these clusters, floating in a sea of stars bound by invisible threads. Feel the gentle pull of gravity and the warm glow of countless suns, each shining with its own story, yet part of a grand, shared cosmic journey. Stars are not just distant points of light. They are the architects and sustainers of life throughout the universe. Their influence extends far beyond their brilliant glow, shaping the environments around them, governing the formation of planets, and providing the essential elements that make life possible. Understanding how stars shape life in the cosmos reveals the deep interconnectedness between these fiery spheres and the very existence of ourselves. At the most fundamental level, stars create the chemical elements that are the building blocks of life. In the intense heat and pressure of their cores, stars fuse simple elements like hydrogen and helium into heavier ones, carbon, nitrogen, oxygen, and beyond. These elements are forged over millions or billions of years and are essential for the chemistry of life as we know it. When stars reach the end of their lives, especially in explosive supernovae or gentle shedding of planetary nebula, they scatter these elements into space, seeding future generations of stars, planets, and potentially living organisms. Our own Sun, a relatively modest star, provides the warmth and energy that sustains life on Earth. Without its steady light, temperatures on our planet would plummet, oceans would freeze, and the delicate balance that allows plants, animals, and humans to thrive would collapse. The sun's light drives photosynthesis, the process by which plants convert sunlight into chemical energy, forming the foundation of most food chains. Beyond warmth, stars influence the very structure and evolution of planetary systems. The gravity of a star shapes the orbits of planets, keeping them in stable paths that allow climates to remain consistent over long periods. The type and variability of a star's radiation affect atmospheric chemistry, climate patterns, and even the potential for habitability. For example, stars that emit strong ultraviolet radiation may strip away planetary atmospheres, while more stable stars offer calm environments where life can develop. The life cycle of stars also contributes to cosmic recycling. When stars die, the material they return to space enriches the interstellar medium with heavy elements. This enriched gas and dust form the raw material for new stars and planets. Over time, this recycling process has increased the abundance of life-essential elements in the universe, making it more hospitable for complex chemistry and biology. In star clusters and galaxies, the collective influence of countless stars creates dynamic environments. Massive stars, with their intense radiation and powerful winds, can trigger waves of star formation by compressing nearby clouds of gas and dust. Conversely, their energetic outbursts can also disperse material, halting star formation in some regions. This interplay shapes the evolution of galaxies, dictating where and when new stars, and potentially new life can arise. Stars also influence life through their variability. Some stars undergo regular pulsations, flares, or dramatic outbursts that can affect the habitability of surrounding planets. Understanding these stellar behaviours is crucial for assessing which exoplanets might harbour life, and for protecting technological civilizations from harmful radiation. On a philosophical level, stars connect us to the universe in profound ways. The elements that compose our bodies, carbon, calcium, iron, were once forged in the hearts of ancient stars. We are, quite literally, made of stardust. This cosmic connection underscores a shared origin and destiny, linking all life to the cycles of stellar birth and death. As you relax and let your thoughts drift, imagine the gentle warmth of a star reaching across the void, nurturing worlds with light and energy. Picture the flow of matter and energy from star to planet to living being, a vast and intricate web of life sustained by the fires of distant suns. In the quiet darkness, stars remind us of our place in the universe, not as isolated beings, but as participants in an ongoing cosmic story. They are the creators, sustainers, and renewers of life, shining beacons in the night that illuminate the path from dust to consciousness. So as you close your eyes and prepare to rest, let the stars' timeless light fill you with a sense of wonder and belonging, a reminder that life itself is shaped and sustained by the majestic power of the stars. The stars that sprinkle the night sky are not just distant, twinkling points of light. They are, in a very real sense, the ancestors of everything that surrounds us, including ourselves. Every atom in your body, every molecule of air you breathe, and every drop of water in the oceans once belonged to a star. This profound connection between stardust and life reveals a cosmic truth. We are all made of stars. The story begins billions of years ago in the hearts of the first generations of stars. These stars, formed from primordial clouds of hydrogen and helium left over from the Big Bang, ignited fusion and forged heavier elements, carbon, oxygen, nitrogen, iron, and many others within their blazing cores. These elements, essential for the chemistry of life, could not have come into existence without the immense pressure and heat inside stars. When massive stars ended their lives in supernova explosions, they scattered these elements across the cosmos. The debris enriched the surrounding space with the raw materials needed to build new stars, planets, and eventually living organisms. Our solar system itself formed from one such cloud of stardust, a mixture of gas and dust infused with elements from countless generations of stars before it. On Earth, these elements came together to create the conditions necessary for life. Carbon atoms formed complex molecules that became the building blocks of cells. Oxygen became part of the air we breathe and the water we drink. Iron, calcium, and phosphorus became components of our blood, bones, and DNA. This intimate relationship means that the stars are not distant strangers, but the very foundation of our existence. This cosmic heritage invites a sense of awe and belonging. When you look up at the night sky, you are looking at distant relatives, ancient furnaces where the elements that make you up were born. The twinkling lights remind us that life on Earth is part of a much larger story, one written in the language of starlight and cosmic cycles. Beyond the physical connection, the idea that we are made of stardust carries a powerful philosophical and spiritual meaning. It speaks to the unity of the universe and the continuity of life. It suggests that in the grand tapestry of existence, nothing is truly separate or isolated. The atoms in your body have travelled through time and space, passed through the hearts of stars, and now live within you. This connection also inspires a sense of responsibility and stewardship. Knowing that we are part of the cosmos encourages us to cherish and protect the planet that supports life, a small but precious home in the vast universe. It reminds us that our actions resonate beyond ourselves, touching the delicate balance of life and matter woven through the stars. As you drift towards sleep, imagine the billions of years and countless journeys that brought the elements inside you from distant stars to this moment. Picture the cosmic forge where carbon and oxygen were born, the explosion that scattered them, and the quiet gathering of stardust that eventually formed our world and your very being. Feel the gentle warmth of this connection, a reminder that the universe is not a cold, empty void, but a living, breathing whole, and that you are a shining part of its endless dance. The stars in their ancient glow carry the story of your existence, illuminating the path from stardust to life. So as your eyes close and your mind quiets, let the knowledge that you are made of stars bring comfort and wonder, a soothing truth from the cosmos to cradle you through the night.